there isn't really a big conceptual jump from polar coordinates to cylindrical coordinates. Cylindrical coordinates, a lot of times I just think of it as polar plus z. It's really just polar in the xy plane, and then you got that z coordinate on there on top. Here I have written the change of coordinates from rectangular coordinates to cylindrical coordinates. So let's just go over how it works. Everything is pretty much the same as in polar. So this angle that opens from the x-axis towards the y-axis, that angle is theta. And then this distance in the xy plane over to the shadow of the point in the xy plane, that's r. And then, so that's basically just, that is just the same thing as polar. And then you go up some distance z right there. So, there it is as an alternative coordinate system. That's how you describe the location of a point in space using r and theta and z. All right, so the rest of this is really just adding the third dimension on top of polar. So let's break down the volume differential. So this distance right here is dr, and then just like in, remember in polar coordinates, when we find this arc length right there, it's going to be r d theta, because the farther you are away from the origin, the bigger the little piece of the polar plane is. So this distance right here is going to be r d theta, and then that height right there is just going to be the change in z. So that's it. That's basically a little cube, and the smaller values for dz and dr and d theta you get, the more this will be. I said cube, it's actually like a little box. And so the way you find the volume of that little box is you just multiply all three of the coordinates. Usually we write this dz r dr d theta, and then this really makes it look like we basically just taken polar coordinates, and stuck a dz there on the end, and that's pretty much what it is. So let me break down some basic examples about how we use this. Okay, I've cooked up what I think is a pretty generic example of an integral, and it's given to us in rectangular coordinates. So if you just look at this integral in rectangular coordinates, when I look at like this limit of integration right there, I'm kind of getting flashbacks to trig sub from Calc 2. So there may be a way to evaluate this in rectangular coordinates, but as soon as you see objects that are involving circles, that should, lead you to think that maybe we ought to try one of these alternative coordinate systems. Okay, so let's try to break this down. So what I see is, when I look at just these parts of that, those are the dx and dy limits of integration. So I just want to try to tackle that first and see what's going on in the xy plane. So if I start with this limit right there, that upper limit of integration is going to be like a y equals something, because that's the second differential there is dy. So I just basically wrote that down, and then I squared both sides and moved the x over, and that gave me a circle of radius 5. Okay, so already I have a circle of radius 5. Now I just need to use the other parts of this limit of integration to decide how much of the circle am I using. Okay, so what I'm going to do is basically just the reverse laser beam method. So since these are dy limits, since these are y limits, I'm going to draw a laser beam that is parallel to the y-axis. According to the setup, this laser beam enters the region at y equals 0. So that means this is the portion of the circle where the region enters. And it leaves at this top y value, which is the top of the circle. So far, I know that I am only using at most the top half of this circle, because a vertical line, a y line, would enter at 0 and exit at the circle. Okay, so I know that I'm using at most the top half of the circle, and let's see if I'm using the entirety of the top half of the circle. Okay, so from this is going to be x limits, so that's going to tell me the range of x values that I am using in order to get, what part of this left and right circle am I using. Okay, so according to this setup right here, if I look at the whole x-axis, I'm not using the whole x-axis. I'm only using the x values that are in between 0 and 5. So that tells me that I am only using that much of the x-axis. So from these limits, I've ruled out using the whole bottom half of the circle. And then from these limits, I've ruled out using the left side of the circle. So in the end, these limits right here, using the reverse laser beam method, only describe that much of the quarter circle. I want to just take a minute to look at some variations of this so you can see some other ways that it could be set up. If I wanted to describe other parts of the circle. Okay, so I've got some other, this isn't like these other two examples. They're not like whole math problems. It's just, I just want to focus on using these X, Y limits to see the different ways that you could describe different parts of this circle. So in this first example here, if I drew a vertical line, just like before here, I'm going from 0 up to the circle. So this time if I drew a vertical line, it would enter at 0 and exit at the circle. So just like the other one, the first one that we did, this is only talking about the top half of the circle. But now when you look at this range for X there, I'm going all the way from -5 all the way on one side of the circle, all the way over to +5 all the way on the other side of the circle. So these limits of integration are actually describing the entire top half of the circle. Okay. All right. Have a look at this one. If you want to, pause the video. It's like a little quiz. Pause the video there and see if you can decide what portion of the circle is shaded in by these limits of integration. Okay. Hopefully you paused the video and you gave it a shot. I'm going to give it away now. Okay. So as before, okay, so now let's look at this like vertical line trick right here. So this time, if I draw this vertical line, I'm actually going to enter at y equals the negative square root of 25 minus x squared. So that's the bottom half of the circle. Now I don't go all the way up to the top half of the circle. This time I only go up to 0. So this time these limits of integration tell me that I'm only talking about the bottom half of the circle. And now these limits of integration here, I am going, what range of this circle, left and right, what part of the x-axis am I using to make the circle? Just the part from -5 to 0. So these limits of integration right here are only describing the bottom part of the circle and also only the left part of the circle. So together, these limits of integration would describe that little quarter circle right there. So hopefully that makes sense how you can kind of use the reverse laser beam method there to decide which parts of the circle you are shading. Okay, so now that we've sussed that out and seen the variations of that, I think that we can, let's jump back to this original problem and try to work out what our r and theta and z limits should be. In the original integral, z is going to go from 0 up to x squared plus y squared. So when I change this over into polar, when I change this over into cylindrical, like I can't even keep it straight because they're so similar to each other. So z goes from 0 up to x squared plus y squared. So now z is going to go from 0 up to, and I wrote r squared there, and I hope you're seeing that that is x squared plus y squared. I'll even go back in and put it in the notes. There. Okay, and now I need to describe the r limits. So in this problem, I'm going to imagine a ray emanating out from the origin, and the origin is included in my region. So I'm going to start with r equals 0, and then it's going to go out to that edge of that circle right there, and that edge of that circle is where r is equal to 5, because remember this 25 right there, that is really r squared. So in this problem, r is equal to 5. And now for the last little bit, I just need to see, so which range of thetas do I sweep out in order to shade that first circle? So that's just like the first 90 degrees right there. So I'm going to go from theta equals 0 out to theta equals pi over 2. I think you can see this range for theta right here. This range for theta is going to be from 0 to pi. And this range for theta down here is actually going to be from pi to 3 pi over 2. Okay, so there's a lot of different variations in this example for you to kind of look at and study. Hopefully it makes sense how you can change. This method actually works to change integrals, double integrals from rectangular into polar, or triple integrals from rectangular into cylindrical. I think this one is just like a real natural use of cylindrical coordinates. You know, hopefully you're starting to catch the drift that when you see x squared plus y squared, that's gonna really be a big hint that this is going to be a cylindrical coordinates problem. So we're asked to find the volumes bounded by these two surfaces. Hopefully when you look at this one here, I can actually see a paraboloid that is facing down that has been shifted up 1 unit. This one, it isn't really obvious what, you know, it's not a quadric surface, so it's not something we've studied already, but I still think it is pretty clear that it is some kind of upward facing thing that has been shifted down. Of course, I had to use Calcplot 3D in order to graph these surfaces. So let's look. This one is the, you know, that one I think is pretty clear. We see that as this kind of downward facing paraboloid. And then the other one here, so it is a lot like a paraboloid. It is sort of like a shape that goes up, except you can see it's kind of a little bit too flat on the bottom there. So let me just try to draw these. Okay, so I basically just sketched my two little surfaces involved in this problem, and let's set up this double integral, and I'm just going to jump straight into cylindrical coordinates. So it starts with dz, so let's imagine a laser beam shooting up parallel to the z-axis. So if we do that, it's going to enter at the shape that's facing up like a bowl, and then it's going to exit right there at the shape that's facing down. That's kind of like an umbrella. So you work inside to out. So this volume is going to be a triple integral of 1, and then since I'm using cylindrical coordinates, it's going to be dz r dr d theta. Okay, so z here is going to be really obvious, right? The bottom one there is the upward facing thing, so this is going to be z equals, and everything has to be in terms of r and theta. So hopefully you see here r squared minus 1 and 1 minus r squared. So it enters at the one that's facing up. So this is going to be this is r squared squared. So this is actually going to be r to the 4th minus 1 up to z equals 1 minus r squared. Okay, all right, that's not so bad. All right, now that we have done z, I can get rid of the 3D picture and just bump this all down to a 2D picture. You know, basically the whole thing just gets smashed. So what I'm looking for is whatever region in the XY plane that would be left if I just sort of smashed these whole things down, you know, like you're crushing a soda can or something. Okay, so where does that happen? Well, that happens when these two surfaces intersect each other. That's the shape that would be left over when it's smashed down like that. So what we need to ask ourselves is, where do those two surfaces intersect each other? Well, they intersect each other when this z is the same value as that z right there. Okay, so I can just plug that in. This is going to be where 1 minus r squared is equal to the bottom one there. That's r to the 4th minus 1. Okay, so this is actually just an equation that's of quadratic form, so I can just solve this. So this is going to be where 0 is equal to r to the 4th plus r squared minus 2. All right, so this factors, so this is where 0 is equal to r squared plus 2, and then r squared minus 1. Okay, so these two surfaces intersect each other either where r is equal to plus or minus the square root of 2i. Okay, so they intersect each other somewhere in the imaginary space, but then, you know, in real space they intersect at plus or minus 1. Okay, so that shape right there where these two things intersect each other really is a circle, and it really is a circle of radius 1. And then, we're looking at this whole solid. It's not like just part of this circle. So all I need to do now is to just describe this circle using polar coordinates. So what I would do here is I would imagine a ray emanating out from the origin. And so I'm just going to imagine this much of the line right there. So that's going to be from where r is equal to 0 out to r is equal to 1. And then if I rotated that line around the whole 2 pi radians, then that would give me the entire circle there. Just to be clear, this isn't the only answer. Another way you could solve this problem is if you're trying to describe a circle, you could do r is in between -1 and 1. But then, if you do the diameter of the circle, you don't have to rotate it a full 360 degrees. You could just do, you'd have to just do 0 to pi, and that would make one circle. So there is multiple ways to set this up correctly, but I just think it's really natural just to imagine one radius and then rotating that all the way around. So this is usually like our default setup for how you describe circle shape regions. So, this one is pretty natural, and I don't think there's any secret about how you work this out, right? You just use Fubini's theorem, so you're literally just doing that integral and getting an answer, and then once you get the answer, you multiply that by r and then integrate with respect to r, and then once you get that answer, you multiply that by theta and integrate that with theta, and it'll just spit out the answer. So, a lot of times problems like this, it's pretty straightforward. I think really the only hard part of this is that kind of inspired idea about how to calculate where these surfaces intersect. All right, I've got another example. I think that this one is a little bit more difficult to imagine. We're asked to find the volume of one shape that's been cut by another shape. So let's start by just kind of trying to piece our way through the given information. So it starts off with this cylinder right here. So hopefully when you look at that cylinder, you can see that it is a cylinder. There's actually two cylinders there, and one of them has radius 1 and the other one has a radius of square root of 5. Okay, so that's basically just two circles, and we're looking at all the radiuses that's in between those circles. So you get a kind of shape like this. Just so you know that the name of this shape, I think it's natural to call it a ring or a washer. In math, we call this an annulus. And then this shape is independent of z. So it's just that same annulus up and down everywhere in the z direction. So we get this kind of shape like this. It's sort of like, I guess, a roll of paper towels, an infinitely tall roll of paper towels. So obviously that has infinite volume, but we're not looking at the whole thing. We're only looking at the piece of it that has been cut by this cone. So that isn't a super easy language to interpret. So if you're confronted with a problem like this, I just want to tell you what they mean when they say something like this is they always mean the finite region. Okay, so if you imagine that I have this kind of infinite paper towel roll, okay, and then I gave it the old samurai sword chop, this piece up here, that piece up there would go on forever. So that can't be what they're talking about, because that region extends to infinity, and there would also be another one down there. So that can't be what they're talking about. So they have to be talking about these two side pieces right there. So I've done my best to draw these. Actually, now that I look at it, I don't think this is quite perfect. Let me try to fix this drawing. Okay, all right, I believe in my 3D drawing right now. It is a bit difficult to imagine this shape. I think I actually messed it up the first time. So basically what I'm imagining is as if somebody sort of like drilled a conical hole out of the top of my infinite paper towel roll. So I'm left with a shape like this. So it was like just two thick walls right there, right? But then somebody chopped them off like that. So it would still have the whole ring around the outside. And then, the ring on the inside is still going to be there, but it's not going to go, it's not going to go over like this and then down because it's been sliced by that piece right there. So that means there's going to be like a little slices taken out of it right there. And that's all the piece that we're going to be left with is something like that on the inside. So I've done my best to draw that over here. So it may not be the easiest region to imagine, but actually it's kind of one of the cool things about math. You don't really need to be able to visualize this in order to be able to set it up. All you need to know is that it's this object is the piece in between the two cones. It's this piece right here that we are left with. Okay, so let's just use our laser beam here and just spit out the answer. So if I imagine shooting a laser beam in parallel to the z-axis, then I will enter right there and exit right there. So this means this was the volume. So I'm going to work inside to outside here. So this is going to be a triple integral of 1, and then this is all in cylindrical coordinates. So I'm going to do dz r dr d theta. Okay, so start off with the z limits. So z is going to go up until it hits the bottom side of this cone. Hopefully you can see just by looking at this right here that I'm actually, what is this? This is going to be plus or minus the square root of 9 times x squared plus y squared, which is going to be plus or minus the square root of 9r squared. So this is actually plus or minus 3r, okay? All right, so those are the z limits. So undo, 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 undo. You guys are waiting for this. All right, so z will go from negative 3r up to positive 3r. All right, and that's it. Now we are done with the 3D picture. So all of this can burn in a fire and boom, we're just back down to our nice little simple annulus picture there. So the rest of this is just describing an annulus in polar coordinates. So let's imagine a ray emanating from the origin here. So actually this time the origin is not inside the figure. The first value of the radius that gives us a point inside the region is r is equal to 1. So I'm going to go from r is equal to 1 out to this exit point right there. So that's going to be r equals the square root of 5. And then we do go all the way around. So this is going to be theta goes from 0 out to theta equals 2 pi. And then just like in the other ones, you just basically, work this whole thing here from inside out. You just start on the inside one and slowly start cranking your way out. So, maybe just for the sake of completeness, let me work this out and put the answer down. I'm not going to go through all of it, but let me just do the work here. Okay, I know I said I wasn't going to break it down, but I've got to break it down. Okay, so what did I do? How did I get the answer? The first thing is I am just doing this little piece right there, right? An antiderivative with respect to z of 1. So I got z. So basically what I'm doing here is z evaluated from negative 3r up to 3r. So this is basically, how did I get that 6r right there? I did 3r minus negative 3r. So I got that 6r right there, okay? Then there is this just magic R that's just produced from our volume differential there. So then this right here is basically just 6r squared. So I added 1 to the power, I got 3. I divided by the result. So 6 divided by 3 is 2. So that's how I got 2r cubed. And then I plugged in square root of 5 and 1. So the square root of 5 is like 5 to the 1/2 power. So that's how I got that 3/2 power right there. And then all of this is just independent of theta. So then basically you just put a theta on the end and then you're going to plug in a 0 and a 2 pi. So that basically just puts a 2 pi out front. So this 2 and that 2 right there gave me this 4 pi. And then, this just came from the plugging in the 5 and plugging in 1. So that's it. That's the volume of this shape. So I don't know, whatever cubic meters or whatever. So, basically the big picture takeaways from this lesson are, first of all, cylindrical coordinates is really just polar. And second of all, the real big picture takeaway is that this thing right here is actually a step in the direction of doing all the kinds of math that we do in terms of a parameterization. That's really, when I look at these formulas, to me, they look like parameterization. So, if you get stuck on a cylindrical coordinates problem, I love these, so just let me know and maybe I can have a look at your problem and try to give you a hint.